All right. Are we training a new cameraman today? Is that what's happening? OK, so welcome to Monday. It's Monday, right? So we have one more week of lectures before spring break. We're going to get through some more stuff about address translation and virtual memory management. Today we're going to keep talking about how we actually translate addresses, and we're going to introduce essentially what is the modern concept of sort of arranging this mapping that we have to perform between the virtual addresses that we expose to processes and actual physical addresses. We're talking about what are called pages. So pages are kind of, so we're going through a couple of design examples of solutions that have certain pros and cons, and pages are kind of where we are. And there's a number of compromises inherent in pages, but the pages are sort of what's in use today. All right? And this isn't working. So the other thing that's happening this week is that there's an assignment due on Friday, right? Yeah. All right. What's that?
I said, wait, what?
Wait, what? Yeah.
Wait, what?
What? Assignment 1's due, right? OK, so
It is, actually.
yeah, it is. So I have some good news and some bad news about that. I want to start with the bad news first. OK. The bad news is, and oh, hi. Turning it on would help. The bad news is that we're going to add some tests to the assignment 2 testing suite to test some brokenness that a couple of bad things that we seem to have noticed people doing, right? So one example, spin locks is locks, right? Do not do this, right? This is not OK. We're going to add a test to catch this. Actually, doing this won't work later, like on assignment 2 period, right? So this will be added to the assignment 1 test suite. The on-demand initialization of standard in and out in read and write that some people are doing, that's Jinghao's fault, by the way. But anyway, we're going to make sure that no one does it anymore. This is also not wrong. And unsynchronized file handles between parent and child, also bad. Also something that we can test for, we think. So at some point, maybe later this week, we're going to actually have, we're going to move the patch target. So when you guys have been creating patches, you've been using this beautiful and yet meaningless string of digits. That's going to change. You're going to have to pull some code from our staff repository and integrate into your system. It should apply completely cleanly. It's the things you shouldn't be changing. But this is going to happen, right? The good news is that we are going to extend the assignment 2 due date until next Friday. How many people think I would actually do that? Come on. No. People are like pulling out their smartphones or like, cancel plan Tahiti, No, actually, we're going to give you till Monday, April 7th. Right? Unless people would prefer the 21st of March. I don't know. I think there was more enthusiasm for the 21st of March than there was for April 7th. That was a joke. No one seemed to get it. Anyway. All right, so simmer down, simmer down. So we're giving you guys 3 weeks, actually over 3 extra weeks on assignment 2. The reason is that you guys are not going to get assignment 2 done this week, right? It's not. I hate to break it to you. There's obviously some magical thinking going on in the class as far as how to approach assignment 2. I'm just sorry, you aren't going to get it done, and I don't want to get a bunch of broken assignment 2s, right? So we're giving you 3+ extra weeks. The assignment 3 due date is not going to change. I can't move that. It's basically the end of the semester. You guys will still have 6 weeks to do assignment 3. That should be enough time. If you're done with assignment 2 now, you can just move on. Right? I hope that this is sunk in, right? I'm actually completely happy to move the deadline because I think the deadline had the effect of at least getting people. How many people started assignment 2? Okay, so you guys have started to understand this is not one of those 115 virtual terrarium assignments that you knock off in like 5 minutes in lab and go home, right? These are hard, right? Assignment 3 is actually a lot harder than assignment 2, right? So please, allocate your time for the rest of the semester with the expectation that you probably still have a lot more to do on assignment 2, and assignment 3 is even more difficult, right? Assignment 3 is much harder, much more difficult to debug, much less specified, much more fun, much more awesome when you get it to work, but difficult. Yeah?
Is the deadline just extended for assignment 2? So
yeah, like I said, I can't move the assignment 3 deadline. The assignment 3 deadline is as far into the end of the semester as I felt comfortable.
0 and 1, should we have all our answers?
Oh, sorry. Yeah, okay, good point. I'm not going to take final submissions for anything until the April 7th, but if you guys haven't started assignment 0, like, please, hopefully that won't matter to anybody. Yeah, but you can certainly go back and fix assignment 1 things. Yeah, James.
We're going to have to resubmit our assignment 1 code again since you're changing the grading.
Actually, what will happen is if you want us to test it again with our new and improved testing suite, you are welcome to resubmit it, right? If you don't, you are welcome to take the grade that you have already, right? I would suggest the latter, right? But we will run the improved lock test. The lock test actually gets run repeatedly as part of both the assignment, I think it does, as it should be, as part of the assignment 2 and assignment 3 testing suites. So any problem, and again, you guys don't want to have problems with your locks. Please come and see the course staff about that. Yeah?
How about the code reading question?
It's everything. You guys can have it's the deadline is the same deadline that was on Friday. Is just now 3.5 weeks later, right? So you guys have time to resubmit the code reading questions, design documents, everything. Okay? Does this make sense, everybody? Yeah, Max. What's that? Was this planned at the beginning of the semester? Is Max's question. No, it wasn't. And actually, I'm worried that next year people won't believe me when I tell them when the assignment 2 due date is, right? Actually, this is sort of, I'll take the blame for this. UB moved the start of the semester, but they didn't move spring break, right? So spring break is actually earlier in the semester than it was last year. I think. I haven't done the math here, but I'm pretty sure. So because spring break is earlier, it's a little bit less time than I thought it would be, right? But no, this was not planned, right? This is an on-demand decision. Any other questions about this? Yeah.
When you test available.
What's that?
When the new test autograd.
I don't know. A couple days. We might not get to over spring break, but.
The scheduling is available.
I don't think we do. I think we test the schedule, or we run something with the alternate schedule. I'll have to look at the testing suite. At some point, we do, I think, try to configure and run with the alternate schedule, but maybe we don't. And I'm surprised that you're asking this, because there is only one group that has actually completed assignment 2 and earned full credit, and that would be Yilong and his partner. So let's give them a round of applause. Yeah, you did. I looked at your patch. Yeah, but it works, so whatever. You don't have to convince me. You just have to convince the autograder, right? And again, we will. So this is an important thing. We will not regrade assignments that have already been submitted. So if you've been submitted and you earned a certain score, you're going to keep that score, right? We will make some changes to, and actually the per point, like nothing about the grading rubrics is going to change. We're going to make some alterations to existing tests to try to test some of these things, right? And so, for example, what it might mean, for example, you lose credit on fork tests because you're not doing your file descriptors right. But that's fine, right? The fork does something to the file table, and so that's important for you guys to get right? Any other questions about this? I should have brought water today. OK. So any questions about address translation? So last time we talked about a couple of different methods of address translation, right? And this was all motivated by our mission of implementing address spaces, which required that we break this connection, this direct connection between addresses and memory, right? So we introduced a level of abstraction, a level of indirection called virtual addresses that act like memory, but require that every one of them be translated. Every time process accesses memory, I need to translate the address. Jing Hao, do me a favor. You'll get me a bottle of water. Sure. Thanks. All right. I'm already tongue-tied and my mouth is dry. So, OK, so we introduced this idea of virtual addresses. They require translation, and we referred to that, and this allowed us to put multiple things behind this interface, right? So we can actually have virtual addresses that point to memory. We can have things to point And ones that point to things that just act like memory, right? Things like files, potentially memory on another machine. And the virtual addresses have much richer semantics, right? So to some degree, what we start to talk about is how does the operating system collaborate with hardware to sort of control these semantics, right? Where is the virtual address? Can it be accessed at this time? And can the process that's trying to translate it access this virtual address, right? But this level of indirection gave us all these nice properties, right? All right, who can describe base and bounds addressing? So we started to talk about the mechanics of actually translating these addresses. So now I've got these virtual addresses, and they don't mean anything, right? And so now, for now, we're talking about times when the virtual addresses are actually going to map to memory somewhere, right? And what I wanted was a way of describing how that mapping works to hardware so that hardware can do it rapidly, right? So base and bounds was by far the simplest way of doing this. How does it work? Yeah.
Check if the virtual address is less than bound, and then we subtract base to get the physical address.
Subtract base. He was so close. Yeah, Kevin. You add the base, yes. So I assign each process a base physical address and a bound. To check whether the virtual address is OK, I just make sure it's below the bound. And to translate it, I just add the base, right? And this maps sort of the the entire process address space to a contiguous chunk of physical memory, right? And that was the problem with it. It was nice and simple, right? Because I only had to tell hardware a couple of things. And it was fast, because it only required a couple of operations to actually perform. This is all going to be done baked into hardware, right? But the problem was that this was a really bad fit for the address space abstraction we were trying to provide, because I couldn't give a process a large amount of contiguous memory that would require I couldn't give a process a large amount of contiguous virtual memory, because that was going to require a large amount of contiguous physical memory, right? So, and that led to significant internal fragmentation, as well as the possibility of external fragmentation as well, right? So this was not a great idea. All right, so then we decided to try to extend this idea by introducing one more piece of state. We called this segmentation. So who can describe how segmentation worked? If one base and bound is not enough, what can I do? Yeah, Damien.
Make a bunch of segments, and then a bunch of bases and bounds.
Yeah, so I use basically, segments are base and bounds. I just use multiple bases and boundsies, right? And each one of those defines what I call a segment, right? So now, and now the nice thing is segments are, we think, at least a good logical fit for address spaces, right? I have a segment with my code in, I have a segment where my stack lives, I have a segment where I've dynamically allocated memory on my heap. So this is kind of a nice idea, right? Everyone can have its own size. They can grow and shrink independently. I can protect them each differently, right, depending on what's inside of them, which is nice. And this is a good way for how processes this is a good fit for how processes typically organize things, right? Typically put all my code together in one place, right? And my stack is somewhere else, and my heap is somewhere else, right? So this was nice. So how does it work? What do I have to do to determine whether or not a virtual address is valid? Or what pieces of what defines a process's virtual memory mappings at this point, right? With base and bounds, every process had a base and a bounds. With segmentation, what does a process have? Yeah, Natasha.
Multiple bases and bounds.
Well, I have multiple bases and bounds, but I actually need something else too, right? For each segment, I need the base virtual address where the segment starts. I need the bounds, which defines the size of the segment. But what else do I need? I need the start. Where?
Oh, in the virtual.
Yeah, but where? What? Starting address where?
In the physical.
Physical address, right? So again, I'm taking a chunk of the process's virtual address space and mapping it to a chunk of physical memory, right? And so I need to know where it starts in virtual memory, where it starts in physical memory, and one size, right? Because the size is going to be the same in both cases, right? So every segment has a start, a base, and a bound. How do I check whether or not a virtual address is valid?
It should lie within the bound of the segment.
It has to be inside some segment, right? So I can loop through my segment table, and I can check to see, does a segment exist such that this virtual address is above the segment start virtual address, but below the start plus the bound, right? So is it inside subsegment? And then how do I translate it once I determine that the address is valid? Sunny. Somebody want to help them out? Paul?
You're asking how to translate the virtual address to the physical?
Yep. I've located a segment. Let's say it's valid, which means I've located a segment that this virtual address is inside.
Right, so it would be the base physical address plus the start minus the base?
Not quite. So I have an address, right? It's the virtual address minus the start, right? That's the offset into the segment. And then I take that and I map it into the physical address space by adding the segment base, right? This type of question is extremely easy to generate for exams. I will just point that out without any further comment, right? I wouldn't say that I love this kind of question, but when it's late at night and you're feeling lazy and you're like, I need one more question for the exam, you're like, OK, I'll do another segmentation question. Very easy, right? Just a little bit of math. So you guys need to know how to do this. OK. The nice thing is sort of similar to the base and bounces, although we've made things a little bit more complicated, right? The translation is still quite direct, right? Thank you. They only accept $1 bills? OK. I owe you $1. I have $1. So the determining whether or not this virtual address is valid requires potentially a number of comparisons, right? Depending on how large the process address space is and how many segments the process has defined, right? And like we said, we can organize things, and it's a nice fit for address spaces. The biggest problem here was that this still required that the entire segment be resident in memory, right? And not just resident, it required that it be contiguous, right? So as soon as a process accessed any part of the segment, I had to grab the segment and put it in memory, right? And grab it where from, we'll get to that, but you guys probably have seen behind the curtain already and determined that things aren't always going to be in memory. Yeah?
This part I kind of don't understand, because if we have multiple segments, even though they're each contiguous, couldn't we just have as many segments as we wanted?
Oh, yeah. So come back to that idea, right? So I think what he's suggesting is, can I make my segments smaller, which will address this problem, right? And yes, I can. But that means that now I'm losing some of the properties of segments I liked, right? So for example, it was nice conceptually to be like, there's a segment with my code in it, right? If I make you have like 10 segments with your code in it to make my layout process a little bit easier, then maybe we're losing that. But that's a nice idea, right? And we'll come back to this, right? But as sort of we've defined it, segmentation is an all or nothing thing, right? And there's potential for both kinds of fragmentation. So certainly I can have external fragmentation if I can't fit a segment into memory because of existing segments. And I might be able to move things around to fix this, but that's a pain. I can also have internal fragmentation. How? What would lead to internal fragmentation? Doug?
If you allocate memory and then you don't use it for a really long time, it's just kind of sitting there.
Well, so in that case, I could take the whole segment and just move it out of memory, right? But what's the problem? Yeah. Oh, yeah, he just flexing his arm. So I can have internal fragmentation, right? If there's a part of the segment, let's say I have a large segment, and part of it is in active use, but there's large parts of it that are not, right? So ideally, I would be able to do something about the parts of that segment that aren't in active use, but I can't because the whole segment has to be present. Gabriel.
How hard would it be to split the segment?
Yeah, OK. I'll just keep going, right? OK, questions about address translation, right? These were the approaches we've described, right? So we liked segmentation. There were things that were nice about it, but this contiguous part was a problem, right? And if we go back to the top, right, remember what we really wanted at the end of the day was the ability to map flexibly and quickly any virtual byte to any physical byte, right? And the part of the sort of the reason that we haven't talked about doing this way is because the operating system can't do this. And so what we started to do are describe limitations of hardware, right? Or sorry, limitations of the operating system that hardware is going to try to help with. And the approaches that we've been discussing are approaches that can be implemented in hardware quite easily, right? But what we haven't talked about is a really, really nice hardware feature that we're going to use to make this process very fast and more flexible than the approaches that we've talked about before, right? So, again, this is one of our common system design principles. If you don't take anything else away from this class, or if you only take a few things, let this be one of them, right? If something is slow, put a cache in front of it. And the cache we're going to use in this case is a special piece of hardware called a translation lookaside buffer. We never call them that again. We call them TLBs because it's so nice to say that word. So TLBs are typically, and there's lots of different TLB designs, but the interface for TLBs is typically, and actually there are a lot of TLB designs, I should say. There's some complexity in this design space. But the simplest way to think about them is they allow you to look something up by its content, right? So we're used to addressing memory by location, right? Give me byte X, byte 10. Content accessible memory allows me to address it by its contents. Give me something else related to the piece of memory that contains this address, right? And we can use this to very quickly and efficiently search for a translation between a virtual and a physical address, right? The content we're going to use for the search is the virtual address, and the answer is going to be the physical address, right? So here's one way to think about this. Here's my TLB, and I've told this particular TLB, and the TLB is part, you can now think of it as sort of being part of the memory management unit, or MMU. So, and what I've told the MMU is, here are 4 virtual to physical translations, right? And you can think of this as just being a virtual, this is virtual byte 10, and it maps to physical byte 50, right? And the operating system is responsible for loading these translations, which allows me to control how virtual addresses for each process are mapped. When I look up an address, right, in this case it's address 800, one way of thinking about it is the TLB is able to simultaneously compare this value against every entry that's been loaded into the TLB, right? And this is done using these fancy hardware tricks. And essentially, this is like a single, a constant overhead operation, right? And in this case, I match against this byte 800. And now the processor knows how to translate that particular virtual address, right? So this is a very neat idea, right? But of course, there's a catch, right? And the catch is that content addressable memory, or TLBs, are limited in size. And actually, I think that the amount of hardware area you have to use to implement a TLB scales as the number of entries squared, or something bad, right? It's like a bad exponential, right? So if you double the size of the cache, you quadruple the amount of area you need on the chip and the amount of transistors you need to actually do these lookups, right? So this is not good. So it means that, we might say, hey, I've got 4 GB of memory. I'll have a CAM with 4 gigabytes of, 4 gigabytes of translation. That way I can translate that'd be awesome, right? You guys are laughing, but that'd be cool, right? But that way I can translate in one cycle any virtual byte to any physical byte, but that CAM would be like the size of the universe or something like that. It'd be very large, right? So we can't do that. So what we do is so at this point, we're sort of faced with a compromise, right? And this is one of those design decisions where there are competing objectives. So remember, segments are too large, essentially. Segments lead to this internal fragmentation, and mapping individual bytes. Now, for example, I could create a hardware architecture that was able to do address translation at the byte level, right? But what it would mean is that the TLB would not be able to cache very many entries, because every byte in the TLB would only map to 1 byte in physical memory. So if I had a TLB with 32 entries, I could only map like 32 bytes of memory, right? That would not be very good. So can we sort of split the difference here, right? Is there a way to create something that's smaller than a segment, right, but large enough to allow TLBs to perform well, right, and to cache enough translations? Because remember, the smaller the TLB is in terms of the amount of virtual memory it can translate, the more often the operating system has to get involved. And the more often the operating system has to get involved, the slower the system goes, right? So the modern solution is to essentially essentially fixed segments, right? You can think of, we call them pages. but you can think of pages as fixed-sized segments, right? And what we try to do is we try to choose a page size that's small enough to limit, so internal fragmentation, so that the contents within a page have some sort of coherence to them, and they're either accessed or not accessed, but large enough to allow these TLBs to map a significant amount of memory, right? Also, there's another overhead to using there's another overhead to doing sort of fixed granularity mappings, which is that there are kernel data structures whose size is going to scale with the number of pages on the system. And we'll talk about those probably on Wednesday, right? The thing that's going to help us here, and we haven't really talked about this property of program execution yet, but there's a very important property that a lot of programs display, which is called locality. What locality means is that if you looked at process memory accesses, and I wish I had like a diagram for this, and I think I said that last year at this point too, but if you look at where processes are accessing memory at a given period of time, what happens is that there's those accesses are extremely clustered within the address space, right? Why is that? Can you guys come up with some explanations for this phenomenon? Yeah.
Because when a process runs, it runs for like a million instructions at a time.
Yeah, but if those million instructions could access a million different bytes of memory, or it could access memory sprinkled randomly all over the process's address space. So what's one thing that leads to spatial locality? Yeah, James.
Well, it's easier when programming to just use an array for something rather than naming like 50 different variables.
OK, so some of the data structures in your program will exhibit spatial locality, right? If you have an array and you have a certain part of your program that's manipulating that array is going to be laid out by the C compiler as contiguous in memory, right? So all of your accesses are now fitting within that array. But what's something even more fundamental about programs, how programs run? Yeah?
Stack and code practice.
What's that?
Stack and code might have the same thing.
No, they're not. The stack and code are totally opposite.
They're constantly in one place.
What's that?
They're always be there.
Well, they're always going to be there, but that doesn't mean my accesses are going to be clustered within them. Doug, you have a theory?
Well, isn't that kind of how we set up memory to begin with? Was we clustered a bunch of different things together in segments? So. OK, so that's a fair point, right? If you think about the entire 4 GB or 2 GB process address space, most of it's not allocated, right? It's actually not mapped. There's a small bit of code over here, small bit of data over here. And so by definition, all of the accesses within my address space have to occur in those little slivers that I've allocated. But it turns out that spatial locality is even better than that, right? It even turns out that the memory accesses are even clustered within the parts of the address space that are valid. What's the reason for this, Gabriel? Yeah, so OK, so the stack is one source of spatial locality, right? When the local variables that you're using within any function are all allocated pretty much right next to each other on the stack, right? So any writes and reads from those local variables are going to be to a very small amount of memory. What's another source?
Loops in the code?
What? OK, not just loops, but it's even better than loops. Like, what is the processor doing? Like, what's the process of executing code? Yeah.
It just goes one address at a time.
Yeah, I mean, a lot of times it's like fetch, decode, execute, +4, right? Like, that's your loop. And then you're at the next instruction. So the only thing, now loops are going to even make this better, right? Because I'm going to go backwards, right? I'm going to stay in a particular region of code. And there are jumps in your code that are going to take you to other parts of, whether if you use like a library function or something like that. But the jumps are pretty, as a fraction of the instructions that are being executed are pretty rare, right? A lot of what you're doing is, EPC, EPC+4. So a lot of those executions are just linear, right? Meaning that just the process of executing instructions itself exhibits a lot of spatial locality, right? Can anyone else think of anything other contributors to locality? I think we've got most of them. So what this means is that because the memory accesses by a process are clustered to within only a small amount of its address space, even a very small cache can be really effective, right? So if my accesses were random, it would mean that in order to work well, the cache that I put, the TLB, would actually have to have a lot of entries in it, right? Because remember, the TLB is limited in size, and so once I fill it up, if the process tries to access a new address, I have to remove something from it, right? But because of spatial locality, it means that even if I have like 32 entries in my TLB or 64 or something like that, I can actually still get a really, really good hit rate on this cache, right? And actually, to make this more effective, there are actually tools that try to optimize for the layout of your binary to make this even less, to make misses in the TLB even less likely, right? So that you can actually, Microsoft, at least when I was there, had a suite of tools where they would take programs, they would run the programs, they would record the jumps within different parts of the code segment, and then they would actually lay out the program differently to try to make all the jumps as small as possible, right? Because if the function that I jump into is right next to the code I'm already executing, that's a big win, as opposed to way far away and somewhere else, okay? Any questions about spatial locality? This is important to understand. This is what makes this whole system work, okay? So the first thing we do in a paging system is we choose a page size, right? 4K is, for years, was sort of like the most common page size. I'm sure that people did all sorts of papers and research and experiments into like what would happen with smaller pages or bigger pages, and no one ever seemed to stop using 4K pages, right? And part of the reason is that there were hardware architectures that actually had some of this baked into them, so it was difficult to change things, but 4K is still in use. I think newer Linux systems actually have support for 64K, like extra big pages and some other types of things, right? As memory's gotten bigger, maybe we'll get bigger pages, right? But 4K is still in use. So if I take 4K pages, and let's say I have 128 entry TLB, what that means is that I can now cache translations for 1 megabyte of memory. Does that make sense? The TLB can store virtual to physical address translations for 128 pages. Each page is 4K in size, meaning that the total amount of memory that TLB can now cache translation for is a megabyte, right? Now, a megabyte doesn't seem like that much, right? My process address space is 4 gigabytes, right? So a megabyte is several orders of magnitude smaller. Why does this work? Because of spatial locality, right? Because that megabyte turns out to be enough to catch a lot of the accesses. But this doesn't seem to make any sense, right? I mean, I just told you that we know that address spaces, there's this huge space between my stack and my code. So how does 1 megabyte doesn't seem like enough? I mean, won't I just end up caching my code or my stack? Well, what would happen with the program that was running and was accessing both its stack and code? What would the TLB look like? What would it fill up with? Ariel. Yeah. So the question is, the address space abstraction means that stuff is like way spread out in my address space, right? So why is a TLB that can cache 1 megabyte of memory sufficient to enable good performance? Well, this means I can cache 1 megabyte of my virtual address space, but what does that 1 megabyte not have to be, Mac?
Quick question about the 1 megabyte.
Yeah.
Isn't it like 5?
Oh no! Yeah. Okay. Sorry. It's 512K. That was just up there to keep you guys honest. Right? Yeah. So that's actually 512 kilobytes of memory. Sorry. So it's even worse. How is this going to work? Right? It's twice as bad as we thought. Kevin.
Well, the translations don't have to be contiguous.
Yeah. So this doesn't have to be contiguous, right? So if I'm accessing, let's say I'm running along and I'm accessing some stuff that's dynamically allocated on my heap and a few local variables on my stack, and of course I'm using the code, and maybe I have some shared libraries. My TLB fills up with entries that are needed to cache all of these parts of my address space, right? So the 512K of memory can be sprinkled anywhere it needs to be, right? And the idea is to use it to cache the entries that are the most used, right? And again, you can think of pages as fixed size segments. The bound is the same for each. So when we go with page size, right? Let me just make sure you guys understand this trade-off. So let's say I was asking you to justify using larger pages, rather than smaller pages? What's good about large pages? Yeah. Yeah, so if let's say I had 8K pages, then I actually could cache 1 megabyte of memory with this system, right, with 128 entries, right? What's bad? Well, what's good about small pages? What's bad about large pages? As pages get bigger and bigger, what's going to happen? Yeah. Well, the nice thing about pages, oh, OK, sorry, which kind of fragmentation? Yeah, exactly. So as the pages get bigger, right, the likelihood that all the page is actually sort of being used in a similar way starts to go down, right? Imagine if my page was the entire size of my address space, then there's no spatial locality left, right? Whereas if my page gets really small, then my spatial locality gets really, really strong, right? I can use one page to catch, one cache entry to catch a lot of translations, right? So that's good. So this is clearly sort of a design trade-off, right? And one of the reasons that systems are moving to bigger pages probably has to do with the fact that programs are getting bigger, there's more memory, and that the larger pages are starting to produce better performance, right? So when we translate pages, we know page translation is so common that we started to come up with some sort of terminology about how to do this, okay? So you can think of, and if you want to map this to segments, right? So remember, each page is a fixed size segment, right? It's a fixed size 4K segment. There's an and you can essentially take any virtual address and you can split it into 2 parts, okay? There's a certain number of bits at the top of the address that identify what page the address is in, okay? And then there's an offset. The offset is everything that's left, right? So in order to translate the page, you could equivalently tell the operating system, I would like page 2 offset 512, right? The offset is always less than what? Page size, right? If the offset was more than the page size, you'd be in the next page, right? So with 4K pages, the offset is always less than 4K. And each virtual page now maps to a physical page, right? There's now a one-to-one mapping. I break up my physical memory into 4K pages. And the way I manage memory is now simply by mapping virtual pages to physical pages, right? Little quiz though, is it sufficient to map a virtual address to a physical page? If I gave you a virtual address, can you map it to a physical address? What more information do you need, Mac?
It doesn't only have meaning within the context of a process.
Right. You need to know what process it is, right? A virtual address by itself means nothing, okay? And then, obviously, all addresses inside one single virtual page map to the same physical page, right? That's where the offset comes into play, okay? And going back to our algorithm, to check whether the page is valid, I take the 32-bit address and I remove the virtual page number, which turns out, you guys will need to know this for assignment 3, and you will know it by heart after assignment 3, right? The top 20 bits are the physical page, or the virtual page number, sorry. The offset is the bottom 12 bits, right? 10 bits for 1K, 2 more bits for 4K, right? Everything else is the top. So I strip off the top 20 bits. I check to see if I've allowed the process to use that virtual page. Now, all my protection is also done on a page granularity, right? I cannot protect an amount of memory smaller than a page. If an operating system, if a process for some reason said, I have this 512 byte data structure that I want you to share with another process and I want to protect it, I can't do that, right? All I can protect is pages, right? So either the other process sees the whole page or nothing, okay? So I check to see if this virtual page is valid. And then all I do is I essentially replace the 20 bits of the address that are the virtual page number with a physical page number. Sometimes we call it a physical frame number, right? So I lop off the top 20 bits, check them to see if there's a mapping. If there is a mapping, I have a new 20 bits, a physical page. I replace those 20 bits, and I'm done, right? Essentially, this is equivalent to taking the physical page and adding the offset, right? But this is usually done by using bitmask because it's nice, OK, so let's walk through an example. Here's my TLB. Assume I'm using 4K pages. Now, at this point, what do I load into the TLB? What is the TLB caching? It's not caching virtual address to physical address translations. What is it caching? Yeah, it's catching virtual page translations to physical pages. Because I don't care about the offset. The offset doesn't change. So the TLB only caches these 20-bit to 20-bit translations, right? And the hardware knows how to do this, right? So the hardware internally understands that when it sees a certain address, it performs that same process of translation we just described. Lops off the top 20 bits, checks in the TLB. If they're there, replaces them with the physical address. If not, what does it do if physical address isn't, if the virtual address is not in the TLB? What does the MMU do? Calls for help, right? Same thing we used to do. Exception, kernel, I need help. I don't know what to do with this address, right? I don't know how to translate this address. OK, so let's go through an example. So, oh, sorry about the hex. So this is OX 800,346. Can someone identify the virtual page number? 800, yes. The bottom 3 nibbles, I think they're actually called nibbles. Yeah, Guru knows. The bottom 3 nibbles are the, each one is 4 bits. That's 12 bits, right? That is the offset. Anything else? The top, potentially up to, oh gosh, I don't know. Anyway, the rest is the virtual page number, right? So my virtual page number is 800. Does the TLB know how to map this virtual page number? Does it? Yeah, it does. It checks, yeah, it maps to everything. No. So remember how CAMs work? This is a single cycle operation. I check everything at once. Ding, 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 I have a winner, right? So how do I translate this address? What's the resulting hex address that I come up with? What's that?
Add the offset to the
Well, you could do that, or you could just tell me what the numbers are, right? It's a little bit easier. It's a string add, right? It's a concatenation, boom, right? Does that make sense? I mapped my virtual page to a physical frame, and I just replaced the top 20 bits. It's pretty simple, actually. This is so yeah. If you wanted to, you could multiply this by 4K and then add that to it, or you could just replace the top bits of the hex thing. A little bit easier, right? All right, and I'm done. So that was nice. What about this guy? What is the virtual page number? It's 10. Do I have a mapping for this in the TLB? Yes, I do. It's 10. Come on. I know. I didn't put a 0 there. That threw you guys off, really? The missing 0? Yeah, you guys are pattern matching. It's like, oh. Page 010 is different from page 10. No, it's the same thing. Right? It was lazy. So there's a missing 0 here. That maps to physical page 50. What's the resulting hex address? 050,336. Yeah, thanks. 050, yeah, right. 336, right? Does this make sense? This is easy, right? All right, let's do another one. Do I have another one? Nope, sorry. OK. But you can imagine how this works. If I can't find the address, I panic. Or I don't panic. I throw an exception. Yeah?
So the actual value that's used to search for the physical address, like the virtual address that's passed to the TLB.
Yep.
Passed to the TLB is the right term. It actually gets modified in place.
Yep.
And returned. Oh, OK.
Yeah, I mean, remember, processes never see physical addresses, right? So when you do a read, like essentially what happens is if you did a read to, OX 10336, right? Before that address hits the memory bus, it's converted by the TLB, right? And then when the result gets back to you, you say, oh, that's nice that that byte is still in OX 10336. But the process has no idea, right? So this translation is occurring at every instruction on the fly, right? Yeah, it's a great question. Any other questions about this? Yeah.
Does the TLB change on contact switches?
Yeah, great question. So does the TLB change on context switches? Let's put it this way. If I don't, given what I've showed you, does this TLB change? Would this TLB have to change on a context switch? Yeah, because this TLB has no way to know what process is running, right? Some TLBs actually have a way to identify, to distinguish between processes, right? So when you use them, you load a process identifier onto the TLB, and that tells the TLB which translations to use, meaning that when you do a context switch, you need to load entries for the new task that's running, but you don't need to get rid of the old ones, right? On this TLB, because it doesn't know how to do that, what would I have to do? What's the only safe thing to do to this TLB every time I have a context switch? Gabriel? Clear it. Just remove all the entries, right? And that's actually, when you guys do assignment 3, you guys will get to do this. And if you do assignment 3 and you want to be awesome, you can actually implement address space IDs on the MIPS process. I wouldn't do that first, but it can be done. It can be done. It's a little bit of extra state. To be honest with you, it actually doesn't help that much. That's the sad thing, right? It's a little bit of a performance improvement, but not a huge one. All right. Yeah, question? I know. I left out the address, the bits that I didn't want. Right? Do you want to look at addresses that are that long? No, I don't. Yeah.
It's like numbers.
It's like I know, but they're hacks. They're scary. They have letters in them. Yeah, I don't use hex addresses. I only use hex addresses that don't have letters in them. I don't know what my address space ends up looking like as a result of that. It's probably a little weird. All right. So how do entries get into the TLB? Yeah, the operating system has to load them, right? So this is, going back to the policy mechanism split, this is the mechanism, right? The TLB is the mechanism, but the TLB doesn't have any idea what to do, right? The operating system has to tell it how to load these addresses, right? So what happens if a process tries to access an address that the TLB does not know how to translate? What's generated? An exception. And it, essentially creates, on your MIPS system, it's actually a special exception called a TLB exception. And probably one of the reasons that certain architectures provided a distinction between these exceptions and other type of exceptions is that TLB exceptions happen all the time, right? Especially when I start running a new process after a context switch. So let's say I clear the TLB after a context switch. What is the first thing that a process will do when it starts to run? Yeah, which will generate a what? Yeah, exactly. So the first thing I do when I start running this, because the TLB knows nothing. It does not know how to translate a single address, right? So as soon as I try to fetch the instruction from the program counter, exception, right? And then the operating system starts the process of loading entries into the TLB as the process generates more TLB faults, right? All right, so looking at paging sort of overall, right? I mean, the great thing about paging is that it maintains the pros of segmentation, right? And in many systems, you actually see systems talk about segments, right? A lot of memory management data structures are actually organized into segments, and then those segments are mapped into pages, right? So I try to sort of preserve the conceptual niceness of segments, which allowed me to sort of apply a single protection scheme, for example, to a whole segment of my address space, but I layer it on top of paging, which gives me better granularity, right? And the greatest thing is that there's, again, there's less internal fragmentation than segmentation because I'm doing this smaller allocation size, right? I don't have to bring in an entire segment just because a process used one part of it. I just bring in the page that the process used, right? Or I just map the page the process used, right? Here's an even awesomer thing, right? No external fragmentation, right? None. If I have a page that I need to allocate in memory, if I have a page available, I've got a page available, right? There is no fit problem, right? Essentially, I've broken my memory just into pages, right? And I just allocate pages, and so the external fragmentation problem is gone, right? Which is pretty nice. The cons of paging are really that in comparison with segments and base and bound, I actually have to tell the hardware a lot more to map the same amount of memory, right? Segmentation, it was like one base and bounds for a segment, and I got essentially an unlimited amount of translations out of that, right? And I also need per page operating system state. So the segment, it was great. It was like, as long as the operating system, an address space might have had like 3 segments in it, right? But address spaces can have thousands of pages in them, right? And for every page, the operating system is going to need to keep some information, allowing it to manage the TLB, right? All right, so we will start with this on Wednesday, and we will talk on Wednesday about the data structures that the operating system uses to maintain state about pages and update the TLB.